Right. So next thing that we are going to consider is binary arithmetic. So we have seen binary numbers. How are we going to do some binary operations? So for example, 1 plus 1. What is this? 1 plus 1. What do we know in decimal? 1 plus 1 is 2. So how do we represent 2 in binary? That's the question. Now, in order to represent 2 in binary, which we are going to see in a minute in the conversion side, but first thing that we need to remember is this is 2, and we have to convert it to binary. Now, how do we convert it to binary? By converting it to binary, that means we have to divide by 2. Okay? So 2 divided by 2 is 1, and then remainder is 0, and 0 divided by 2 is going to be 0. So we can say that 2 can be represented as 1, 0. Or if you want, take this one, 1, 0, 2 to the power 0, 2 to the power 1. This is going to be 0. 2 to the power 1 is 2. So that means 1 plus 1 will give us 0, and then we have got a carry 1, which will come down as 1, 0. Okay, 0 plus 1, or 1 plus 0, it's going to give us 1. Okay, and the carry is 0, so it's going to be 0, 1. Now, one thing that we need to understand, if we are adding two binary numbers, that means like 0 plus 0, or 0 plus 1, or 1 plus 0, or 1 plus 1. These are all valid operations. So we have got two binary numbers, 4 possibilities. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1, it's 2. And these are the outputs that we are going to get. Okay? If we are using, and with 2, we have seen that, so 0, 0, this is 0, 1, this is 0, 1, and this is 1, 0. That means by using two binary numbers, we are going to get 2 digits of binaries, okay? 2 digits. If we are using 3 binary numbers, we have got 2 to the power 3, 8 possibilities, and we need to use 3 bits to represent each of those binary numbers. So for example, 1 plus 1 plus 1, let's say, it's not actually going to give you 3 bits, but way of representing is 1 plus 1 plus 1 is 3. So how to represent 3? Again, by dividing by 2, you're going to get 1 as a remainder, and 1 divided by 2, and then it's going to be 0.5, and so on. So 1 plus 1 plus 1, it's actually going to give you 3 as 1, 1. So 1, 1 to the power 0 to the power 1. So this is 1, this is 2, 2 plus 1, 3. Okay? Now, you can see that by using, when we generally do this in a truth table, AB as a variables 0, 0, 0, 1, 1, 0, 1, 1. This is 0, this is 1, this is 2, and this is 3. Okay? So with 2 bits, we represent 4 digits. With 3 bits, we represent 8 bits. 8 bits, 0 to 7. And with 4 bits, we represent 0 to 15. Okay? So this is how it goes. All right then. So let's see the arithmetic operation where this line has to be over here, 55 plus 55, 110. Now, how do we do this in binary? Now, if we go through this one, 1 plus 1, we know that it's 2. So 0 is written, we have got a carry. 1 plus 0 plus 1, again it's 2, so 0 is written, and we have got another carry. 1 plus 1 plus 1, we know that it's 3. 1 is written, and we have got another carry. 1 plus 1 is 2, 0 is written, we have got another carry. 3, 1 is written, we have got another carry. 1 plus 1 is 2, 0 is written, and we have got another carry, and that will be written down as well. Then if you want to convert it, you can check it if you have done the right operation. So this is how we do the addition. We are just adding bit by bit. Let's try another one. 110 and 011, for example. Just a simple one. This is going to give you, this is 6 if you want to convert it, and this is going to be 3, which we are expecting 9. So 1 plus 0, it's 1. Then 1 plus 1, it is 2, so 0 is written. And we have got a carry. 1 plus 1, it's again 2, so we just write 0, and we have got a carry. And then that carry is going to drop down, and we have got 9. So is this 9? 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. So 8 is valid, 2 to the power 3 is 8, and 1 is valid. These are zeros. So 8 plus 1 will give you 9. This is how we do the addition. How about subtraction? Now, subtraction. Now, in addition, as you can see, we have got carries. So when this one is done, if we have a larger number, we put the carry on the next one uses the carry, and so forth. Then in subtract operation, we do a borrow. So if we have a number which is less than, we have to borrow, right? So that's what we are going to do. So 1 minus 1, it's going to be 0. Similar as the decimal ones. Now, 0 minus 1, it's not possible. I have to borrow. I have to borrow from the neighbor. Now, the question comes in. How much do I need to borrow from here? So, if you think about a decimal operation, let's say 72 minus 15. So this one has to borrow from here. So how much does it borrow? This is in base 10. It borrows 10. So this becomes 12, right? Then 12 minus 5, it's going to be 7. And this becomes 6. And then 6 minus 1 is going to be 57. Okay? So 5, and that's going to be 57. Now, the same applies for the binary numbers. If we are going to borrow from here, this becomes 2. 2 minus 1, it's going to be 1. Okay, and this is going to be 0. We deducted 1 because we already borrowed it. Now, then, this is 0. 0 minus 1 means it has to borrow from here. Then this becomes 0, and this becomes 2. 2 minus 1, it's 1 again. So this is now 0. So 0, 0, it's going to be 0. Then this one, 0 minus 1, neighbor doesn't have anything, so we have to borrow from the other one. So when we borrow from here, this is going to be 0. First, this is going to be 2. Then this one has to borrow from here. Okay? So this becomes 2, and that borrows 2. 2 minus 1, 1. and as it was 2 and you just borrowed it, this becomes 1, and 1 minus 0, it's going to be 1. Okay, and this is 0, sorry, this is 0, and this will be 0. Okay, now you can have the subtrend as larger than the median, so subtract the median from the subtrend and add or assign a minus sign to the result. That's also possible. So if you have any problems with these of understanding while we are having the live lecture, face-to-face lectures, then you can ask me and I can go through that again. Okay, so binary arithmetic, we carry on with the multiplication. Now, multiplication, again, it's very easy because we just have ones and zeros. If you multiply something with 0, you are going to get 0. If you multiply something with 1, you're just going to get the same value. So 0 times everything over here, it's going to give us 0. 1 time everything over here, then it's going to give us 1. This has to be here, it's shifted a lot. Then 0 again, then 1 again, and that's it. And then what we do, we add them together. So this is shifted a lot, this has to be here, so that 1, then this is going to be 1 as well, then 1 plus 1, 0. Okay, then 1 is a carry over here, then 1 plus 1, 0 again, and another carry, 1 plus 1 plus 1, it's 1, and the carry, then it's 1 and 1. Okay, so it's like a repeated addition of either the shifted version of the multiplicand, if the corresponding multiplier digit is 1, or 0 if the multiplier digit is 0. So this is known as bit by bit multiplication. Now, the last one that we are going to see as a binary operation is the division. Now, how do we do division? It's a little bit tricky and you have to be really careful. Now we have got the divisor on one side and dividend on the other side. We have to check each of these individual bits if it is greater than or equal to. Okay, so we start with 1. Is 1 greater than or equal to the divisor, 1011? It's no. Then we get another digit, 10. Is it greater? No. Then we get another digit, 100. Is it greater? No. Another digit, so 4-digit 1001 is greater than 1011? No. So we got another digit. Now 10010, it's greater than. We have got 5 digits over here. There's 4 digits. It looks like it's greater. So we put 1 over here. And then we subtract this divisor from the dividend. So that's the first quotient that we are getting. And 1011 will be subtracted. Then we got 0111. Then we drop down another 0 over here. Now 1110, is it greater than the divisor? Yes, it is. So we subtract the divisor from the dividend. That means this is 1 and that's going to be subtracted. So we have got 0011. Then we drop down another 0, 110. Is it greater? No, so it's 0. Then another one, 1101. Yes, it's greater. So that means this is going to be 1 and you just subtract that. And we get 210 as a reminder of this remainder of this equation operation. So we have to check one by one until we get the enough digits and it's greater than or equal to the divisor. Then if it is greater than or equal to the divisor, we put 1 to the quotient. Okay? So this is how we perform the division operation. Okay then, so another important thing is, how do we do the conversions? So if we have a different basis, then how do we use those bases? So for example, if you want to convert from decimal to binary, binary to decimal, octal to decimal, decimal to octal, hexadecimal to decimal, decimal to hexadecimal, or octal to hexadecimal, or binary to hexadecimal, and vice versa. So these are all alternatives over here. And it's also possible. It can be any other base. It doesn't need to be fixed, any of those. In computer digital systems, we generally use these bases. That's why I gave the example based on that. So what do we do? If we have a decimal decimal to binary conversion, that means we need to consider base 10 to base 2. Okay? So as we are using base 2, as I already said before, if you have a number over here, let's say a, you have to divide it by 2 until it reaches to the 0 that you cannot perform any other division anymore. Okay? So then you get the remainder, either 0 or 1 as a coefficient, and then we take the quotient and we repeat the division. Okay? I can show you an example of that in a minute. Now, this is one way of doing this. And another short method that I generally use is based on the powers. So what you can do is you can find the greatest number, that is power of 2, and that produces a positive difference, n. And when subtracted from n, then you apply the same and you just repeat it until you reach to the end. So 729, for example. What is the maximum possible power of 2 that we can use? If you do remember, 2 to the power 9 is giving us 512. 2 to the power 10 is giving us 124. So we cannot use 124 because it's much more larger. We just need the closer, largest possible power. So 2 to the power 9 is that one. So 2 to the power 9 is, so we can say 729 minus 2 to the power 9, which is 512. This is going to give us 217. So we got the first number, 2 to the power 9. What you can do is 2 to the power 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So that means 2 to the power 9, it's going to be 1. Let's carry on. Then we have got 217. What is the largest possible power that we can use in order to cover 217? So 256 is 2 to the power 8, which is larger. Then we need 2 to the power 7, which is 128. So that means 8 is going to be 0, but 7 it's going to be 1, which is going to be 128. So 217 minus 128, it's going to be 89. Then we take that 89. What is the largest? 2 to the power 6, 64. Yes, so we can use 64. That means 2 to the power 6 will be 1. And then this is going to be 64. So 89 minus 64 is going to be 25. Then we get 25. 2 to the power 5 is 32. So that's going to be 0. 2 to the power 4 is 16. So 16 can be done. So we can say minus 16, which is equivalent to 9. Then 9 to the power 3 is 8, so it's going to be 1. So that's going to be 9 minus 8, it's going to be 1. And we just need 1 now. So in order to get 1, this is going to be 0, this is going to be 0, this is going to be 1. Okay, so then we end up 1 minus 1, which is 0. So this is the value of 729 in base 2. Okay, for larger numbers, this is easier to use. I don't generally use these operations, so I just draw this, and you can use, if you want, you can write it down. If you want, you can do it in your mind, and you can easily calculate it, but that just needs a practice. So if you have a smaller number and you want to use division that I mentioned, so for example, 13 as base 10 has to be converted to base 2. This is not too large, so you don't need to do too many divisions over here. So 13 divided by 2. We need a quotient, we need a remainder, and we need a coefficient. These are the three things that we are looking. So 13 divided by 2, quotient, it's going to be 6. Remainder, it's going to be 1. Coefficient is same as the remainder, so it's going to be 1 as well. Then we got 6, so that 6 comes down, divided by 2. This is going to be 3. Any remainder? No. The coefficient is going to be 0 as well. Then 3 comes down, divided by 2. Then it's going to be 1. Remainder, it's also 1. So that means coefficient is also 1. Then 1 divided by 2. Quotient is 0. Remainder, it's going to be 1. And then this is going to be 1 as well. Now, if this value is an integer, there are no fractions. This is important. We are reading from bottom to top. So this is going to be 1101. If you want, you can try and convert it back to decimal. You will see that you are going to get 13. Okay, so equivalent to 13 in base 10. So this is decimal conversion, decimal to binary conversion. If you have a fractional number, you just need to multiply by 2 rather than dividing by 2. So this is the same example that we have done. And if you want to find the fractional part, let's say 13.625, then 625 has to be multiplied by 2, which is 1.25. And then we get 0.25. The coefficient is 1, so it's going to be 1 here. And then 0.25 multiplied by 2, 0.5. Then this is going to be 0. And 0.5 is taken, multiplied by 2, 1.0. As this is 0, we cannot carry on. This is 1, and that's written already. So we have got the fractional. We read from top to bottom, opposite of the integers. Top to bottom, 101, so 0.101 is the answer. So this is how we can do the base conversion of an integer or a decimal to the binary. Again, we can repeat the same thing using a base 8. Okay, so 175 base 10. If you want to convert it to base 8, you just need to divide by base 8. 175 divided by 8, 21. Remainder is 7, so that means coefficient is also 7. Then we take 21 divided by 8, quotient is 2, remainder is 5, okay? And then this is going to be 5. Then 2 divided by 8, it's 0, remainder is 2, then it is 2. Again, we are reading from bottom to top. 257 is the octal equivalent of 175. And the fraction, you just need to multiply by 8 in order to convert it to octal, base 8. Then we can do the same thing with other bases as well. This is one way of doing this. So for example, when we consider octal numbers, now octal numbers are actually representing 2 to the power 3, which is 8. These are the octal numbers. Now, 0 to 7 that we are talking about. Now, how do we represent? We need 3 bits in order to represent 8 possibilities. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 100, 101, 110, 111. So 0, 1, 2, 3, 4, 5, 6, 7. This is base 8. So maximum that you can get in base 8, 2 to the power 3 is 8. So this is going to be 111. If you convert it to decimal, you will see that you are going to get 7. Okay, now the question is, based on the octals, if we have got a binary number and we want to convert it to octal, let's say 1, 0, 0, 1.0111. Okay, this is in binary and I want to convert it to octal. Now, as I want to represent in octal, that means if I group binary numbers by 3 bits, that will give me a octal equivalent. So 001, starting from decimal point to the left, it's going to be 1. Then this one left alone, but I need 3 bits. So I just put extra zeros over there. Then it's another 001, it's also 1. Then from point to the left, point to the right, 011, it's going to be 3. And then 1 left, so we add zeros, 100, it's going to be 4. So 11.34 is actually our base 8 conversion of that number. And if you want, you can do the same thing other way around. Let's say 27.45. We just need to get individually, okay, based on this. So 2 is 0, 1, 0. Always 3 bits for octal. Okay, this is in octal. 7 is 111. 0.4 is 100. And 5 is 101. So this is in binary. You don't need to do anything else. Now, octal to binary, binary to octal, it's pretty straightforward. 3 bits, either you group them or you just represent the octal number with 3 bits of that binary. Then hexadecimal, hexa is 2 to the power 4, which is 16. So that means we need to use 4 bits. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and it goes down to 1, 1, 1, 1. So this is 0, 1, 2, 3, and 15, or F, we call it. So once again, it's similar approach as the octal. Let's say we have got 1, 1, 0, 1, 0, 0.11101. Now, in octal, we were grouping by 3 bits. Now, in hexadecimal, we'll group by 4 bits. Okay, again, group by 4 bits and add another zeros to make it 4 bits as well. So this is 1010. If you want, you can do the conversion or you can do it in your mind. This is going to be 10, which is A, and this is 1. Then 1110, again, this is in hexadecimal, it's going to be E, and then the rest will be 100, it's going to be 8. So this is the hexadecimal equivalent of this binary number. If we have a hexadecimal number, then let's say 7AF.3B. 7, what is it? 0111. A, 1010. F, 1111. Don't worry about it. You will get used to it and you will learn them. Then 3 is 0111, 0011. And B is 1010. 1, 1. Okay, so our base 2 number is 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1. Okay, we consider all of those. So either hexadecimal to binary or binary to hexadecimal. Again, it's quite straightforward, and you can find these in these slides as well. So in the end, we have this table showing all of them in decimal, octal, hexadecimal, and binary number. Once again, you should not remember them. You should understand how to convert from different bases into binary or from binary to different bases. Okay, so this is the rule for it.